Okay, my talk is about Riometer. And so the contents of my presentation, I have some introductory remarks. I'm going to talk very, very briefly about the ionosphere and absorption in the ionosphere. And then hopefully, if we have time, I'll get into the riometer that we recently built at HAARP, the High Frequency Active Auroral Research Program up in Gakona, Alaska. And I have some observations from that. It's so new that I don't have a lot of observations, but I'll show you what I have. And if we have time, I'll also do a little bit of a couple slides on historical applications of the rheometer. So a rheometer is an acronym for Relative Ionospheric Opacity Meter. Now, not to be outdone, someone had to extend that out to call it a relative ionospheric opacity meter for extraterrestrial emissions of radio noise. I don't know who comes up with this stuff, but that's what it is. And electrically and mechanically, it's a very stable receiver and antenna system. And its job is to measure the absorption in the D region of the ionosphere. And the signal source is the galactic synchrotron radiation that pervades the Milky Way. And this device is also called the cosmic noise technique. So what we're looking at then is we have the galactic background radiation that pervades the Milky Way. It propagates to the Earth and penetrates the ionosphere. And if there's no absorption in the D region, which is where you normally would get your absorption, if there is none, then you will receive the background radiation with your antenna. You have a receiver and a processor, and then you have a display of the data and archiving of the data for later study. If there is absorption, then the galactic background radiation does not penetrate or penetrates weakly. And so that shows up in your daily data that you use. Now, for us, it's very, very useful at high latitudes because at the HAARP project, we use an ionosonde to determine the critical frequency of the ionosphere above the HAARP facility. And that frequency is very important to almost all of the experiments we do. The trouble is that if there's absorption, then the ionosonde does not get up into the upper levels of the ionosphere that we're interested in. So the absorption itself may render the ionosonde useless. So what we do is we combine the two of them, and so we have an ionosonde. It's called a digisonde, made by Lowell Observatory, and it's on site at the facility along with the rheometer. So these two devices, the rheometer and ionosonde, complement each other. And to give us a more complete picture of the local ionosphere for experiments. Now, the rheometer then provides information about the D region and specifically the absorption in the D region. And then the ionosonde provides information about the ionosphere above the D region, which is what we're most interested in. So the galactic background radiation, there's lots of names given for this, just like just about anything in any technical field. There's all kinds of names that mean the same thing. Cosmic noise, galactic noise, cosmic radio noise, cosmic background radiation. I'm going to try to call it galactic background radiation. And what it is there are free electrons out in the Milky Way, and they're trapped by pretty weak magnetic field lines in the interstellar medium. And when they're trapped, they're going, and if they're moving, which they are, they will spiral and corkscrew around the magnetic field line. And so this corkscrewing motion then is an acceleration of the electron, which causes it to radiate. So there's an enormous number of electrons out there that are spiraling around and radiating, that it becomes a continuum of frequencies over a pretty wide range. And I'll talk a little bit more about that later. The radii of these electrons in their spiral motion are in the neighborhood of hundreds of millions of kilometers, and with a period of in the neighborhood of 1 hour. Of course, there's a very, very wide range of that, but that's kind of a working number. Now, the observed background radiation is the strongest when the Milky Way is centered over the antenna's beam. And for a fixed broadbeam antenna like what we use at HAARP, the plot of the radiation then has a broad peak, and it varies over a 24-hour period as the Milky Way drifts in and out of the beam. So it's essentially a drift mode instrument. Now, this peak in the radiation that we receive occurs about 4 minutes earlier because of the differences between the solar and sidereal days. So this graphic here shows you what's going on as the Earth moves. The faraway star or radiation that we're looking at does not move, whereas the sun shows up in a 24-hour period, but that star shows up 23 hours and 56 minutes roughly. Now, what's important about this plot here? This is from NASA, and it shows the ionosphere over here on the right-hand part of the plot, and the D region is shown down here at the lower part. E region and F region are the three regions shown here. The electron density is shown as this red trace that goes up, and then you have the oxygen and nitrogen on the other three traces. And you'll notice that the D region, in the D region, the electron density is fairly low compared to what it would be up at the F and E regions. But what's important is that the density of the neutral particles is pretty high down at these low altitudes. And so that opens up the possibility of collisions between the electrons and these neutral particles, the oxygen and nitrogen and so forth. And so when you have collisions, then you have absorption. So we know that the ionosphere consists of free electrons and positive ions in equal numbers, and this is called a plasma. It's electrically neutral by definition. Now, these ions and electrons coexist with neutral particles, but the neutral particles far outnumber them, as shown on that previous graph, and the chance of collision between electrons and neutral particles is relatively high at those lower altitudes. Now, we know that the atmosphere's density and collision rate vary with altitude, so you would expect the absorption to also vary with altitude. And by the way, the D region is in the neighborhood of about 50 kilometers on up to 90, 95 kilometers altitude above Earth's surface. So if you have this galactic background radiation, it's going to penetrate all the way down to the D region and to the ground if there's no absorption. But if there's any absorption in the D region, then the radiation from the galactic background then is going to be essentially absorbed and blocked from being received on the ground. There are a lot of things that affect the electron density, the position of the sun in the sky, the latitude, the season of the year, and the progress of the solar cycle. So all of those parameters really complicate the actual application and use of a rheometer. Now, as far as the absorption goes, there's uh, the reasons for the absorption are called agents, and there are three primary agents that lead to absorption in the D region, and I'll describe those in just a second. Um, these uh, these so-called agents affect the ionosphere in different ways depending on the latitude. And when we see absorption caused by these so-called agents, what they show up as are relatively short events in the absorption, and they can last from maybe a few minutes to a few hours. They're random and irregular, but I have seen some quasi-periodic events that coincide with auroral substorms, and that's something that's unique to higher latitudes where I'm located. Now, at low latitudes, the latitudes below 60 degrees magnetic, the solar flare is one of the primary agents of absorption. And so what we have from the solar flare then is a sudden increase in electron density, and that causes a significant and rapid change in the absorption because now we have more electrons that have a higher probability of colliding with a neutral particle in the atmosphere. So when this occurs, the D region then becomes opaque to HF radio waves, and we call that a radio blackout. And generally, the radio waves at lower frequencies in the HF band are most affected. We also see these as sudden ionospheric disturbances in when we're monitoring VLF transmitter propagation with a very low frequency receiver. So what we have then is we'll have a solar flare as shown on this D region absorption prediction plot from from NOAA, and so we'll have pretty heavy. If we had a rheometer in say located somewhere where this red area is, which depicts the flare, the solar flare effects on Earth, then we would see heavy absorption at the lower latitudes from that. And you can, if you have a rheometer or the capability of measuring the galactic background at lower latitudes, you can use the GOES X-ray flux plots to correlate with your rheometer uh, absorption plots that you're making. Now, at higher latitudes, the problem with the X-rays is that they don't penetrate deep enough into the ionosphere to affect the D region. So very seldom do we see any kind of absorption due to an X-ray flare on the sun at higher latitudes. So that brings us into agent one uh, for high latitude absorption, and that is the solar energetic particle event, or it's SEP event. And this is also called solar particle event, solar radiation storm, and it's mostly protons that are ejected by the sun and accelerated by some method on the sun. And when those protons then come and hit Earth, they are able to penetrate the magnetosphere, but they become trapped by magnetic field lines, the Earth's magnetic field lines, and they spiral around. And when they do that, then they precipitate down into the higher latitude ionosphere, into the D region. They increase the electron density, and then the collision rate increases, and so does the absorption. So the SEP event are fairly rare. They usually are only felt within about 20 degrees of the poles. And so, in other words, latitude 70 and above generally is where this is felt most significantly. And when this happens, it's called a polar cap absorption event or a PCA. And now, even though Anchorage and HAARP facility and these parts of Alaska are at considered higher latitudes, the solar energetic particle events are so rare, and even when they do occur, we may not even see them where we are at HAARP. So that brings us to agent number two, and that is the particle precipitation. And this is also called auroral precipitation. And it's caused by, uh, first, by magnetic reconnection or merging of the interplanetary magnetic field and Earth's magnetic field. And when that happens, then energetic electrons in the solar wind are able to penetrate down into the magnetosphere. They follow magnetic field lines at higher latitudes and come down, collide with neutral particles, ionize them, which increases the electron density and then the possibility of collisions and absorption. So the main source of these electrons and are coronal hole high-speed streams and coronal mass ejections. And now last month we had CME after CME after CME. Right now we're seeing coronal hole high-speed streams, almost a continuous a stream of streams that are causing absorption in higher latitude ionosphere up here where I'm located. Now, this particle precipitation occurs around the auroral oval, and that the auroral oval, shown in green and yellow over here on the right-hand side, is the footprint of open magnetic field lines. Now, these are magnetic field lines that have been opened because of the magnetic disturbance associated with coronal mass ejection or a high-speed stream. And so if you look at this map, you can see that the auroral oval, if you have a riometer in this below this auroral oval, then you're going to see absorption during a magnetic disturbance. And this oval expands toward the equator when there is a magnetic disturbance. And during quiet times, magnetically quiet times, the oval will shrink and become just a fairly thin band at very high latitude. But whenever there's a disturbance, it'll expand as shown here in this plot. So these types of events from particle precipitation or auroral precipitation are far more common than SEP events. In fact, I don't think a day has gone by in the last 6 weeks or so that I haven't seen at least one of these. Now, I have a couple plots here and this is just an example of real data that I've taken from the HAARP. The upper two plots are, one is that the blue trace is 30 megahertz, and the green trace is 38.2 megahertz. The orange trace that you see is what we call a quiet day curve, and I'm going to talk a little bit about that later. But you can see that this absorption event shown by this dip in both the blue and green traces lines up perfectly with this bay or dip in the magnetic field. So this lower plot is a magnetogram from my magnetometer that I have up at HAARP. And this bay then is an indicator that there was a change in the auroral electrojet, which was changed by the electron density increasing, and then that led to higher absorption and the dips at these two frequencies that you see above. Now, the time correlation is almost perfect on these, and there are some other characteristics of this dip in the absorption, and I'll talk a little bit about that later. Now, one thing you should notice is that the grid on these plots is fairly narrow. For example, this upper plot at 30 megahertz, each one of these grid lines is a half a dB. So the rheometer has to be pretty sensitive in order to receive or be able to detect the differences in a non-absorption ionosphere and one that is active. Now, I just have a couple of things I want to say about rheometer design is, for one thing, the frequency of the rheometer, the receiver frequency, has to be well above the critical frequency of the ionosphere's F region. That's because we want to be able to receive the galactic background radiation, and we want to be well above the F region because the F region could potentially reflect or deflect, refract the background radiation. So we're always going to be above in the high HF or low VHF region. And when you look at this and think about, okay, well, a lower frequency gives us more sensitivity, but that means a bigger antenna for a given beam width. And when you compare all of these alternatives, you come up with a compromised frequency range of rheometers of 25 to 50 megahertz. So that's become kind of the standard range these days for rheometers. And this is really important that even though our rheometer operates at, say, 30 megahertz or so, then at HAARP, we need to reduce that frequency down to the operating range of the HAARP transmitter, which is 2.7 to 10 megahertz. So we have to somehow change the data that we see that on the rheometer to something that's useful in our frequency range. And it's been found that the absorption goes approximately as the inverse frequency squared. So if we know what the rheometer frequency is operating at, say 30 megahertz, and we know what the transmitter frequency we want to use, we can reduce that using this formula. It's not perfect, but it's a good working formula that we use pretty much every time. Here's an example. Let's say the absorption at 30 megahertz was measured to be 1 dB. And using that formula in a previous slide, that means the absorption at 10 megahertz is 9 dB, and at 3 megahertz is 100 dB. So a lot of our experiments use the frequencies down in the 3 megahertz range. And when this is when you have 100 dB of absorption, that means you don't have an experiment. So we have to move on to do something else. That exponent 2 in the frequency may not apply always. It's been found to vary from, say, 1.4 to 2.2, but 2 is something you can do in your head. It's easy to square a number in your head. It's not easy to square a 1.8 or something like that. At least I can't do that. So when we're talking about a rheometer, there's two things that we need to know. First, we're going to compare the disturbed ionosphere to an undisturbed ionosphere. And that means that we need to know what the received signal would have been without absorption. And this brings us to the quiet day curve, or QDC. And that's kind of a fundamental part of a rheometer, is the quiet day curve. A quiet day curve is always based on post-processed data. So it can be out of date before you even use it. And so what that means is that you need to follow the three P's: patience, patience, and patience. That's what it takes to build a working QDC. Also, you have noisy data, you have RFI, and all of that kind of thing to contend with. Now, this plot here is from the University of Alaska Fairbanks riometer back in September of 1965. And this is back from in the days when they used paper charts. And someone had plotted a whole bunch of data and came up with a quiet day curve, which you can see is this black line that follows an S-type shape. Now, it turns out that September of 1965 was the month I started electrical engineering in the electrical engineering department at the University of Alaska. I was a freshman student in double E at University of Alaska in Fairbanks, and I didn't even know any of this was going on at the time. So one of the problems with the QDC is there's a lot of ways to determine a QDC. If you take the same data and use and apply each one of these methods, you'll come up with a slightly different curve shape. So the actual method you end up using at any given riometer becomes a matter of judgment. And and by judgment, I mean really experience of something I don't have a lot of. So I'm trying to learn from people that actually know what they're doing. And another thing that needs to be realized is that if you have a small error in your QDC, then that leads to a much larger error at the frequency of interest, which in our case is between roughly 3 and 10 megahertz. And each frequency channel, if you have a multi-channel riometer, it's going to have its own QDC. Now, here's a plot at 30 megahertz. This is back on the 5th of February, just 5 weeks ago or so. The orange trace is your quiet day curve. And this was developed after a few weeks of data. I think it was about 3 weeks of data. And you can see that at least in this area here, the blue trace, which is the actual received galactic background radiation at 30 megahertz, follows it pretty good. You can see there was a couple of absorption events over here toward the right. And then as we get over in this area, we see a bunch of what looks like noise. In fact, we have received energy that's higher than the quiet day. So how can that be? Well, we think this was caused by RFI. We don't know the source of the RFI, and we later changed this frequency of this channel to 30.3, and that definitely did improve it. So I'll show you more of that later. This is the same date and time for the 38.2 megahertz channel. And you can see the quiet day curve is the orange trace. You can see the absorption events over here at about 1800 or so, 17 to 1800. And you'll notice that there is still some interference at 38.2 megahertz, but it's not as severe as it was for on the 30 megahertz channel. So there's a lot of things that affect the quiet day curve. If you have, for example, the sun's 27-day rotation period, you'll have maybe coronal holes that are persistent that go through several rotations. And each time one of those becomes in view of the Earth, then you're going to have problems, magnetic disturbances caused by that. The solar cycle itself changes on a 11-year and 20-year to 22-year period. You're going to have problems due to that. You have solar activity, flaring, and other activity during any given time period. And then you have the seasonal effects as well. Now, I mentioned earlier that the riometer operates in the drift scan mode. So when we're talking about design, we need to also consider the antenna. And so the signal at the receiver is the average of the antenna's entire beam at any given time. And most of riometers use a directional antenna. They're as a directional antenna, it's pointed straight up to the zenith, and that makes it relatively insensitive to distant RFI that's being propagated in. And then a narrow beam antenna is giving you a good view of directly overhead without any influence from non-zenith directions. So in other words, if you're interested in what's happening directly above, like we are at HAARP, then and we don't care or don't want to have the influence of non-zenith directions, then we would want to have a highly directional antenna. Now, early riometers and even today used Yagi antennas, usually in a relatively small array of Yagis, and a Yagi is a minimum of two elements, but usually there's going to be they'll use a four or maybe even a five element Yagi antenna. And I'll show you more if I have time to get into the history of riometers at HAARP. So the HAARP riometer itself is over here in the southern part of Alaska, shown here. I don't know if you can see this, but this is HAARP here where my mouse is, and Anchorage is where I am right now. About 100 miles, 180 miles east-northeast of Anchorage, and about 125 miles or so from the Canadian border. And the magnetic latitude is almost 64 degrees north. It's near Gakona, Alaska. It's a small village, um, uh, about 180, or actually about 200 road miles from Anchorage. And this aerial view that I'm showing on the right here is from approximately 15,000 feet. So it's almost 3 miles across the width. And you can see that this is the HAARP facility. It encompasses this whole area here. Here is the ionospheric research instrument, the big transmitter itself. And the operations center is down here. The riometer that we just installed here in January is located up on Science Pad 3, which is up here in the upper left quadrant. The riometer that we're using is made by Keo Scientific in Calgary, and it's called their model Keo Rio. So we actually purchased this back in July of 2024, and but delivery lead times, we've finally received the receiver itself in January, or I'm sorry, in December, and we installed it in January. It's a two-channel broadbeam type. It uses a single LWA antenna. Now, Craig Taylor talked about the LWA. Well, we've taken that antenna, the same antenna, and adopted it for a lot of other uses. And one of them is this riometer. The frequencies were set initially to 30.0 and 38.2, and we later adjusted that lower one for RFI up to 30.3. They operated a nominal 250 kilohertz bandwidth, and the advertised stability of this unit, which we have not verified, is 0.01 dB stability over an 8-hour period. And that's pretty phenomenal when you think about it. It's pretty hard to make a receiver that does that. Here's a picture of the controller, and it's rack mounted, 3.5 inches high, and the block diagram is shown here. And you can see a lot of familiar components. There's a single board computer that is running a Linux operating system in the upper left here. you have three receivers. You have a channel 1 and channel 2 sky receivers, and then you have a reference receiver that's hooked to a noise source. And that's used for comparison. And that's one of the things that helps improve the stability of this device. And you got your power supplies and your coupling devices to get you out to the antenna, and then the antenna itself, which is an active antenna. This is a photograph of the riometer, of the inside of it. And here's the single board computer in the upper left. And here are the three receivers down here in roughly in the middle. The Sky and Sky 2, those are the two radio channels. And then we have the reference channel that's down here at the lower channel, and the coupling to get us out to the antenna, and a linear power supply that powers the uh, electronics in the antenna itself. And then we have a switch mode power supply over here that operates the computer. Now the front end electronics, the active part of the antenna is a dual preamplifier because there's two dipoles out there. And so it's a dual amplifier located right at the antenna and connected directly to the dipole elements. And it has a heater built into it so that it controls the temperature of the front end electronics to hopefully improve their stability. And the heater is designed to keep the electronics at a higher temperature than the highest anticipated ambient temperature. And at HAARP, the temperatures can get in the neighborhood of 90 degrees Fahrenheit during the summertime, and during winter can get easily down to a minus 40 Fahrenheit. This is a picture of the preamp, and it looks very much like the stock LWA preamp, but it's not. It's a more or less a redesigned unit. There's a lot of commonality, but it was redesigned specifically by Keo for this application. It's mounted in the hub, the antenna hub base, which is this plastic element down underneath. The heater is on this board here, and then the two amplifiers are a sandwich of two printed circuit boards up here at the top. The antenna itself is mechanically identical to the LWA antenna. So basically it's a stock antenna, and the only thing that makes it different is the front end electronics that's located up in the hub at the very top at the apex of the dipole. So you have two dipoles here and these triangular shaped aluminum frames, and they're supported by fiberglass insulated rods in about the middle of the mast here. And then there's a ground stake that you drive into the ground and fasten the steel mast to that. And I'll show you some pictures of that here in right now, I guess. So here's where we're starting out doing the installation. Now I'm the guy taking the pictures, so I'm just standing around shouting orders. And you'll notice that he's driving the mast, and this fellow over here on the right is he's all bundled up, and this fellow over on the left is not bundled up. And I'll show you another picture here where they're both bundled up. And this was back in July of 2024 when we were doing this, and it wasn't cold at all, but there was just hordes and hordes of mosquitoes. And so Evans on the left, he is an old-time Alaskan, and he knows all about the mosquitoes, so he got bundled up right away. Evan over here on the right, he's I think from Massachusetts and has only been there for a few months at the time, and so he learned his lesson and got himself bundled up against those mosquitoes. So went together really fast. Maybe a half an hour or so to assemble it. And so here's a view of the antenna itself. It's about a meter and a half high, about 5 feet. And in the background, you can see there's optical domes and other equipment that's used during HAARP experiments there. And then this view is the same antenna that I took in September of last year, and this shows the coaxial cable that goes back to the receiver. And it's actually enclosed in a flexible conduit there to keep from being chewed on by foxes and rodents. This is a picture of the actual receiver itself mounted in a rack. This is a GPS receiver on the site and some local area network equipment, and then the monitor and keyboard. Now, you don't need a monitor and keyboard to actually operate it. It sure makes it easier to set it up, and but once it's set up, you basically can disconnect all this stuff, and it'll just sit there and run 24/7. Here's a screenshot of the desktop, and you can select the frequency spectrum over about a 250 kilohertz bandwidth. You can select the channel 1 or channel 2 to display. You can set it to do max hold and so on. And then down below here, you have a relative sky noise plot that the red is channel 2, the blue is channel 1. And so that just gives you a kind of a reading that you can use. So let's look at some observations. Am I doing okay on time?
You're about at the end of your time, so
I am okay. Well, let me just show this animation here. This is of the various observations over about a 1 month period. And you can see that the traces are all over the place. And the orange trace comes and goes. And that's because we're still experimenting with that, trying to come up with a decent quiet day curve. But that shows what we got there. Now this is I'll show this as the last one. This plot is the only plot that I have seen in almost 8 weeks now that looks halfway decent. There's been a nonstop absorption events since we installed the device. But on the 3rd of March, we got a couple traces that only had a few little burbles in them. So this is more or less what a quiet day would look like. Is you have a minimum in around 1000 UTC and a peak in the neighborhood of 1800 UTC. So that brings me to the end of my time, and I'll be glad to answer questions. If you want, you can put your questions in the chat, and I'll try to answer them through the chat.
thank you, Whit. Thank you.
Yeah, you're welcome. Thank you.